I'm Braxton Lopez, and this is our Project 1 video. The first step in our procedure design was to get two cylinders of different materials with holes drilled in the middle of them. And the purpose of having two different materials was to have different material properties, such as K values and density, and then we would estimate the H values based off of the parameters that the assignment gave us. We measured the temperature of the air coming out of the heat gun that we would use to heat the cylinders to get a airstream temperature. And then we started with our design setup. And as you can see here, we have a thermocouple underneath the styrofoam in the middle of the cylinder, and then we have a thermocouple taped to the front of the cylinder that's getting that direct stream of air. And then after we set this up, we turn on the heat gun. We have the insulation so that we can approximate it as an infinite length cylinder, and that allows us to use our models later on. And then we took measurements every 20 seconds, and that's how we recorded our data. We did it manually. And then we repeat for steps 4 through 6 for the second specimen.
Awesome. And so here are our measured results. Now, obviously, there's some differences between the steady state temperatures, and there's several reasons for this, both because of the material properties, and also it's important to note that for the aluminum specimen, we actually had to scoot the heat gun significantly farther away from the cylinder, because in our first experiment with aluminum, it started melting the styrofoam on top, which would no longer allow us to approximate it as an infinite cylinder. So we scooched it back, which lowered our H values as well as our steady state temperature. Now, we also approximated our results using the lumped capacitance method and the first term approximation, and you can see those results here. As you can see, our BO numbers are both below 0.1, so while we didn't technically need to do the first term approximation, the results are graphed here and their approximations. Now, it is important to note once again that for aluminum, our H value was different because of how far we scooted the heat gun away from the cylinder. Now, the assignment listed that we could use parameters of H between 20 and 45. This is with a H of 20, and so a real model that would more closely simulate our measured results would have a H value of a lot lower, probably around about 15. And so there's some discrepancies between that. And then our results for still 1018 are listed as well, and those model really well.
All right, and so these are our takeaways and our insights from this. First of all, you'll notice that the lump capacitance on the steel, or that green dotted line, shows that the temperature between the surface measured and the middle of the cylinder measured. And we're okay with this because the lump capacitance assumes a constant temperature throughout the cylinder as it's heating up. And then the first term approximation matches the surface temperature, which is also the purpose for that. And so that is consistent. And then on our other one, we had some difficulty approximating the first term approximation, so we ended up just going with the lump capacitance because we were within parameters on the BO and the 4 years number. And it's important to note that the lump capacitance way overshoots it, and Braxton mentioned that this was because of our H values that were within the parameters we were giving for the assignment, but we believe were inaccurate because we had to scoot the heat gun away so it wouldn't melt the styrofoam. And to solve this in future experiments, we would use different insulation as well as a better H value, and this would give us better accuracy on that other on the aluminum. And then finally, that last point just notes that we are satisfied with our lump capacitance because of the BO numbers and the 4 years numbers. And if those didn't allow, we would do a better job on the first term approximation.